July. So yes, I will talk on correspondence theory. It's part of my thesis. And as Nicola already said, I will focus on the Hilbert space case. Nevertheless, since I'm heavily interested also in the non-Hilbert space case, so for arbitrary P, I will at least mention at some points that these results can be proven essentially the same way in the non-Hilbert space case. In particular, because some of the results I will show seem quite trivial in the Hilbert space case due to some general C-star algebraic results, but you'll see then. So on Cn, we consider these family of probability measures for each positive t. We take the measure mu t to be, well, the integral or the Lebesgue measure weighted by this Gaussian normalized to a probability measure. And the space LT2 is just the L2 space with respect to this measure. And the Fock space FT2 is just the subspace of holomorphic functions in this LT2 space. And as you probably all know, this is a closed subspace. So the Fock space FT2 is a Hilbert space itself. It's a lot more. It's, well, a reproducing kernel Hilbert space. So for each point from Cn, say Z, the point is called Z, then you can just write the point evaluations of functions in the Fock space by pairing the function against some other function, which is usually called the reproducing kernel, KZT. And well, this kernel can be computed. It's just this exponential. And once we have the reproducing kernel, we can also write down the normalized reproducing kernel, which is just the reproducing kernel divided by its norm. So we get an element of norm 1. And an immediate consequence of the existence of the kernels is that the orthogonal projection from the L2 space to the Fock space is pointwise just given by pairing the function with the reproducing kernel. And this in turn can just be written out as this integral operator. This is all I want to tell you on the Fock space, I think. There's of course a bunch of more stuff I could tell you, but let's keep it to the very minimum. Let's define Toeplitz operators. So if we have a function from Cn to C, say measurable bounded, then we define the Toeplitz operator Tf, so a Toeplitz operator with symbol f, on the Fock space by acting as follows. If we apply to a function g from the Fock space, we multiply g with a symbol, which gives us, since f is bounded, an element in L2, and then project back to the Fock space. These are Toeplitz operators, and we also have the Berzin transform. So if we start with a bounded operator on the Fock space, then the Berzin transform of A tilde is a function from Cn to C, and it's defined pointwise by just applying the operator to the normalized kernel and then pair it again with the kernel. This is the Berzin transform, and with the Berzin transform of an operator, we also have the Berzin transform of a function, which is defined by simply the Berzin transform of the Toeplitz operator with symbol f. And since there is a choice here, we can choose the parameter t. We have to fix that in the notation of the Berzin transform of the function. All right, so these are Toeplitz operators and Berzin transforms. By the way, if you have any questions, if I'm too fast, you can always just interrupt me. Just interrupt me then. All right, so what else is there on the Fock space? We have group actions of Cn. I'm going to define those now. So first of all, for setting up the group actions, I need the while operators. The while operator wz for z a fixed point from Cn is defined by, well, if you apply to function f, what happens is you shift the argument of f by z, and afterwards multiplied by the normalized reproducing kernel at z. And these while operators turn out to be unitary, and the inverse is just given by the while operator at the inverse point. Further, which is quite important, is that the map z goes to wz is continuous in, well, at least in strong operator topology, not in norm topology, but in strong operator topology. This can be shown quite easily. And well, if you take the product of two while operators, you have the following. If you compose the while operator at z with the while operator at w, you get the while operator at z plus w, well, except for some constant factor. And this constant can be, well, it's not really important what precisely it is. It is of norm 1. And well, if you exchange the rules or the positions of z and y, you get the complex conjugate. So in principle, what this tells you is that you get a projective representation of Cn on the Fock space. If you don't like the word projective representation, then just ignore it. It's not really important. What this means, just so you know. And now let's come to the actual group actions. So we have group actions of Cn on functions and on operators. So if we have a function from Cn to C, then we define the group action alpha of Cn by alpha z of f is just the function where the argument is shifted by z. And the group action on the operator A, a bounded operator from the Fock space, is simply defined by adjoining with the while operators in this way. And well, usually we will apply the group action for functions, not for functions from the Fock space, but for symbols. So say L infinity functions. And well, those two group actions are closely related in the following way. If you apply the group action to a Toeplitz operator, then what you get is the Toeplitz operator where the symbol is just shifted by z. And similarly, if you apply the group action to the Beresin transform of an operator, you get the Beresin transform of the shifted operator. So this already shows, if you want to understand Toeplitz operators on the Fock space, it's a really good idea to consider these group actions. All right, and so these actions will be very basic in everything that follows. So if you want to remember something from the first 5 slides, take these two group actions. And just on a side note, the group actions are, of course, not norm continuous on L infinity or the bounded functions. Well, they have some weaker continuity properties. On L infinity, they are weak star continuous, and on the bounded operators, they are continuous and strong operator topology, but that's not really important. So we consider the subspaces or the subalgebras of elements where these shifts are actually norm continuous. So C0 is the set of all L infinity functions on Cn such that the shift of f z goes to alpha zf is continuous in supremum norm. And C1 will be the set of all bounded linear operators on the Fock space such that z goes to alpha z of a is continuous in operator norm. Now,
Robert,
yes?
for C naught, say bounded uniformly continuous will work?
Exactly. So C0 is just the bounded uniformly continuous functions. Okay. That's very easy to show. So I will never write C0 in the following. I will always write BUC. But understanding C1 is actually not that easy. We will see plenty of operators that are in there, but here's one example of operator which is not in there in C1. So if you take U, the operator which maps f of z to f of minus z, then one can show that this is actually not in C1. So this is not the whole algebra of bounded operators. Okay, and also we will see this operator U again later. So my talk will be, I announced it as being on correspondence theory, and correspondence theory is a part of something called quantum harmonic analysis. And this quantum harmonic analysis was invented by Reinhard Werner in '84, and he set things up in the Schrödinger representation, so bounded operators on L2 of Rn. And indeed, you can take his results and translate it into the Siegel-Bachmann or the Fock space setting by just applying the Bachmann transform, or you can set it up directly in this setting. And as it turns out, this quantum harmonic analysis, whatever it is, I will explain it in a second, is a very powerful tool to study Toeplitz operators on Fock spaces, not only in the Hilbert space setting, also in the P-Fock space setting, but that I will talk about. And yeah, the main goal of this talk is at least sketching or explaining what quantum harmonic analysis is and how it applies to the study of Toeplitz operators. So quantum harmonic analysis in principle is about convolution. So let's start with well, the classical convolution of two integral functions. If we have f and g L1 functions on Cn, then as you all know, their convolution is defined like this. So pointwise as this integral. This is usually how you define it, but you could equally well define the convolution in this way. The convolution of f and g is defined by integrating f against the group action of Cn at g. So here you have to know that w goes to alpha w of g. This is continuous in L1, and therefore this integral here is well defined as a Bochner integral in L1. And in case you are not familiar with Bochner integrals, that's not really a big problem. Just imagine something like a Banach space value Lebesgue integration theory. And as long as your Banach space is separable, it's really not much more than that. If it's non-separable, there are some issues with measurability, but I will not go into detail here. Everything works out in the end for Bochner integrals in my setting. So just think Lebesgue integration somehow in a Banach space kind of way. Well, since this shift acts continuously in L1, this is well defined as an L1 valued integral. And if you know this, you can try to define other kinds of convolutions. So for example, these kinds of convolutions. If we start with, say, two trace class operators on the Fock space, so this n of ft is for me always trace class, then we can define the convolution of A with f1. F is still from L1 here. Convolution of A and F is the same as convolution of F and A, is simply integrating the group action of Cn, the group action at A against F. And here you have to know that this map is also continuous in trace class, that you can prove. It's not really hard to see. Therefore, this is well defined as a Bochner integral. And we can also define the convolution of two trace class operators. This is a function from Cn to C, and the convolution of A and B at point Z is defined as the trace, the trace class trace of A alpha Z of UBU.
Robert,
yes.
One question.
Yes.
What is the reason of this conjugation of the U with U?
Well, I would say it's for historic reasons, because Reinhard Werner did it in his initial paper like this. You could do the same thing without the U. It's just that the formulas you get in the end change by adjoining U in several places, but you can do the same theory without having U here. It's just historically like this, I would say. It's not really important having U there.
It's just following this original paper.
Exactly. So you can do it without the U here, and then you have to do the obvious changes in the formulas, but everything works out in the same way.
Mm-hmm.
So you have these three kinds of convolutions. You have the convolution of two integrable functions, the convolution of an integrable function with a trace class operator, and the convolution of two trace class operators.
I'm sorry, one question.
Yes.
In the definition of the convolution of A and F,
yes,
is it equivalent to apply the group action to the function F?
Well, then you have to worry about integrability stuff. So what you're asking is, maybe if I make some space here, if this is the same as alpha V F A,
yes,
something like this.
Yes.
But here it's not really clear if this exists as a Bochner integral. So you don't have any much integrability conditions here. So this is really the way you should do it. Otherwise, you have to worry if the integral exists. Well, that's not really clear. So this is just the better way of setting things up.
Okay, thank you.
Now, of course, these convolutions have just a bunch of nice properties. Otherwise, we would not study them. Just here's some properties of the classical convolutions. So if we take the convolution of two functions, the L1 norm of that is less than the product of the L1 norms. And if you integrate the convolution, what you get is in the end just the product of the two integrals. You have similar properties for the new convolutions. So if you take the convolution of a function, L1 function and a trace class operator, what you get is a trace class operator, and the trace class norm of that is less than the L1 norm of the function and the trace norm of the operator. And if you take the trace of the convolution, what you get is the integral over the function times the trace of the operator. This is actually not not that hard to see. What is more hard and rather technical to prove is the third point. If you take the L1 norm of the convolution of two functions, you can estimate this by this constant times the product of the two trace norms. And if you integrate over the convolution, then what you get is the same constant times the product of the traces. So this is rather technical. And what else do you get is the usual properties. You have like linearity in each argument. The convolution is associative, it's commutative. And also the convolution is well behaved with respect to the group actions, so with respect to the shifts. So for example, you can write alpha z of the convolution is the same as the convolution of alpha zf with a, or the convolution of f with alpha za. So these things all work out as one might expect.
Wait a minute, you said the convolution is commutative, so a times b is equal b times a.
Yes, so a times b is b times a. Well, on this level, commutativity, this is the only real commutativity statement we have, because the other were defined commutative. So this was by definition the same.
Yes.
So this is really the only commutative property you have to prove. And here actually, this is also not hard. If you just look at the formula, this is rather clear that this is commutative. What is more involved is the associativity, in particular, the associativity when it comes to the convolution of three operators. So proving that this is the same as this. This is rather involved, but nevertheless, it's true. So for this, you have to work a bit. Okay, now for the classical convolution, as you know, you don't need to restrict it to L1 factors. You can also define this as a map from L1 times L infinity to L infinity. So simply by the same formula, but you could also define this convolution by one of the following two approaches, which are closely related, either by convolution, defining the convolution as this integral, and well, this is not a Bochner integral anymore, this integral exists as a weak star integral, or what is which is closely related, you could do the following. You could observe that for two integrable functions, their convolution defines this identity. So if you integrate the convolution of those two guys against some other integrable function, this is the same as integrating, say, g against the convolution of u, f, and h. So this you can just show with Fubini. And well, this identity is what we will, okay, so you have this for f and g in L1. And now if you want to define the convolution where the second factor is in L infinity, you use that L infinity is the dual of L1. And then you say that the convolution of f and g, sorry? Okay. You define the convolution of f and g as the unique function L infinity, which defines this duality relation. And this actually works out and gives you the same convolution. And this duality, starting from this duality relation, is the way we will extend the convolution to the second factor being not trace class anymore. So, as I said, we want to extend this notion of convolution now. So we start with the first factor, say f or a is either integrable or trace class. And I think there's a phone call going on somewhere. And the second factor should be either integrable or a bounded linear operator. And then we want to define these convolutions, either integrating an integrable function against a bounded operator or a trace class operator against a bounded function, or trace class operator against a bounded operator. And we will do this using, again, the dualities, dual of L1 is L infinity, or dual of the trace class operators under the trace duality is just the bounded operators. And the key to this is just these identities, which always hold true if B or G is either trace class or integrable, and for B or G, either a bounded linear operator or just a bounded function, we use these relations as the defining relations for the for the convolutions. So the convolution of f and b is the unique element in the bounded linear operators satisfying this relation, and similar, the convolution of a and g is defined in of a and b. And well, actually this gives you something meaningful, because it inherits a bunch of nice properties from the convolutions we had before, and I don't want to go into the details here. We have still commutativity in the first factor, so maybe if you have something like this, a times b times c, so if a and b are trace class, and c is a bounded linear operator, then this is, for example, the same as the convolution of a with the convolution of b and c. And you get properties of this kind, which you of course have to prove, but everything goes through. You have to work a bit here again, it's a bit technical, but it all works as you expected. The convolutions give you the same properties you know from the classical convolutions. And just as a side note, in the classical convolutions, you are not restricted to the second factor being integrable or L infinity. You can also have the second factor being in LP for any p, and then you get a convolution from L1 times LP to LP, and you get the same thing here. This is not the most important point, so I'll just give a short remark on this. You get by interpolation a convolution from L1 plus trace class times LP plus, this is now the P Schatten class, to the 2 LP plus the P Schatten class, just as a side note. But if you don't like Schatten classes, just think about the L1 trace class and L infinity bounded operator thing. So now what, or how does this help us with Toeplitz operators? There are a couple of very particular identities that relate all these convolutional stuff to Toeplitz operators. Let's look at the following very simple trace class operator. The operator PC, as I denote it, is just the tensor of the constant function 1 with the constant function 1. So it acts as PC of f is just f1, 1. And the constant function 1 is just a reproducing kernel at 0. So this is just f0 considered as the constant function in the Fock space. This is what this PC does. And RT is just a certain normalized version of this trace class operator PC. And with this operator, we have the following important properties. If we start with a function f, say in LP, well, you can either think P is 1 or infinity if you don't want the intermediate spaces. For all these functions, we have that the convolution of this RT with f is simply the Toeplitz operator with symbol f. And similar, if we have a bounded linear operator A, then the convolution of PC with A is simply the Berzin transform of A. So these two identities really relate quantum harmonic analysis with the study of Toeplitz operators. And just as a side note, from this you immediately get, with the usual norm estimates for convolutions, the following two facts which you usually have to work somewhat for. If you have a symbol in LP, then the Toeplitz operator is in the P Schatten class. And also if you have an operator in the P Schatten class, then the Berzin transform is in LP. For these two facts, you usually have to work a bit on the Fock space, and using this convolution results or this convolution approach, you get these results more or less for free.
Robert, one question. These properties was already known, or it is from your PhD?
So these were known before. So, well, say in the Hilbert space case, they were known. For example, they are on the shoe book on Fock spaces. I think, well, in the non-Hilbert space setting, it's already the question what a Schatten class is. With the convolution approach, you can also show them in the non-Hilbert space setting, but on the Fock space, on the Hilbert space, they are not new. They are well known. The point here is that with the convolutions, you get those properties a lot easier. So this is my point here. They are not really new. They are just easier to prove in this way. I don't know due to whom they are. I guess they were also contained in some papers by KSU, but well, you can easily prove it in this way. Also,
Sorry.
Charlie,
Sorry, I have a question.
Yes.
In the previous, the definition of the Toeplitz operator with an arbitrary symbol F in LP, is it different from the normal definition with a bounded, essentially bounded function, or
No, it's well, the problem here is if you just have a symbol which is in a, well, just to answer your question, the definition is the same in the sense that it's defined by the as the same integral operator. Now, the problem is
integral operator with the kernel, with the reproducing kernel.
Exactly. It's just the same formula. So TFG of Z is just defined as the integral G of W F of W e to the Z W over T d mu T of W. Just this integral expression is defining the Toeplitz operator. Now, if the symbol is not in L infinity, if it's just say in L1, it's a priori not clear that this is a bounded operator. This you usually have to prove. If you're in L1, then you get a bounded operator, but you get this also for free from this result. So this in particular implies boundedness if you have an L1 symbol. This is not trivial.
Okay, thank you.
Another thing you get is the following. If you start from an L infinity symbol, then the Toeplitz operator is in C1. So this can be a bit surprising. Just to recall, C1 is the set of all operators that the Z goes to alpha Z of A is uniformly continuous. So if we would say that F is in the bounded uniformly continuous functions, this would be clear because then we have that the operator norm of F minus alpha Z with the Toeplitz operator norm of this is just the same as operator norm of the Toeplitz operator F minus alpha Z F, which can be estimated by the uniform norm of F minus alpha Z F, which goes to 0 for Z to 0. This only works for bounded uniformly continuous symbols. So it's really a bit surprising that this is actually true. Toeplitz operator is in C1 for every essentially bounded symbol. But the proof is now very short. First, note that continuity is sufficient to prove continuity at 0, because otherwise you can always adjoin while operators, so you arrive at 0. And then you can do the following. If you apply the shift to the Toeplitz operator and subtract the Toeplitz operator, this is the same as applying the shift to this convolution and subtracting the convolution, because as I have just said, this is just the same as the Toeplitz operator. And now you can pull by the properties of the convolution the shift to the first factor here, to this trace class operator. Use the linearity of the convolution. So this here is just the same as convolving the shift of RT minus RT with a symbol. Now you use the standard norm estimates for convolutions. So you estimate this by the trace norm of the shift of RT minus RT times the supremum norm of F. And now since the shift is continuous in trace class norm, this goes to 0 for W to 0. So we get this seemingly very non-trivial result by some very elementary properties of convolutions. Not elementary in the way that they are proven elementarily, but they are very naive properties of the convolutions. This you get very easily. All right. So this is this. Now let's come to correspondence theory, which is a subpart of quantum harmonic analysis, which can be done once we understand all these convolutions. So first of all, I want to note, which is not really surprising, if we start with an L1 function and an operator in C1, then the convolution is just the same as we expect. We integrate the group action on A against F. This exists again as a Bochner integral and gives you an element again in C1. So what you can say is that this convolution gives you an L1 module structure on C1 if you want. Also note the following. If we start with some operator A, bounded linear operator, And we look at the Toeplitz operator, the symbol of which is the Beresin transform of A. By the identities I have shown you, this is the same as convolving this operator